Welcome back to Decouple. Today I'm joined by returning guest Zeke Hausfather, who is the Director of Climate and Energy at the Breakthrough Institute. Zeke is a climate scientist whose research focuses on observational temperature records, climate models, and mitigation technologies. He has master's degrees in environmental science from Yale University and Vrije Universiteit in Amsterdam, and a PhD in climate science from the University of California, Berkeley. Zeke, I understand you've also contributed to this most recent IPCC report that we're here to discuss today. For folks who didn't hear our first interview together, it was a smash hit on Decouple. Go back and check that out for sure for a backgrounder. But again, today we're going to be talking about this sixth assessment report. Before we get into that, Zeke, let's just get into something casual. Like, you've been busy this week. Just fill us in on how you've been doing, how you've responded to this. I know psychologically, I spend a lot of time focused on solutions, and it's it's a little less intense, but I find weeks like this for me get a little bit intense as I have a 2.5-year-old son, and I think about what 2100 means for him and these kind of abstract numbers. How have you been holding up, my friend?
Yeah, I mean, it's always a challenge, and part of it is that the IPCC process is focused on problems before solutions, right? We have a working group 3 report that'll be out about a year from now that is all about the solution side of the equation. It's a lot more positive. But yeah, it's been an intense week, both in the lead up to the report, trying to finish a bunch of last minute analysis based on earlier drafts. And then, once it was out, sort of everyone in the world wanting to talk about it, and all the conversations and all the nuanced points, because it's a big report. This is a 4,000-page report. There was 260 lead authors, another 550 or so contributing authors, of which I was one of them. It covers, almost everything in the sort of physical climate science space. And so, I even can't admit to having read the entire report, though I've skimmed through most of the chapters, and certainly read the summary for policymakers and technical summary in line by line detail. But if folks want to get, a bit more background on the report itself, I helped Carbon Brief put together a Q&A that covers a lot of the major issues. Though, ironically, at 22,000 words, the Q&A we wrote is actually longer than the summary for policymakers of the new report.
Which is, I think, 45 pages. So, yeah. A lot to wade through. And, I have to admit myself as well, my research for this episode has been pretty cursory, and a lot of it's been checking out your Twitter feeds, which has also been very informative. So let's dive into it a little bit. It seems like the big takeaways that I've gotten is that we have a sort of greater resolution now in terms of probabilities and temperature ranges. Seems like that's coming into focus a little bit. We now understand, I'm not sure if this is a newsflash, but that, the human impact is, the certain cause for climate changes that we're seeing. We should be in a natural cooling cycle. What else was there here? It seemed like there's an increased ability to attribute extreme weather events to climate change. Am I missing anything major here before we sort of dive into the details?
So those are all big ones. There is also a lot more focus in this report around just when the world might pass particular warming levels, like 1.5 or 2 degrees. They've been the focus of a lot of the sort of international discussions in the Paris Agreement. There have been some revisions to our understanding of historical warming that are important in sort of the remaining carbon budget and all these sort of things. Better inclusion of Earth system feedbacks and their uncertainties in some of these estimates. The list can go on and on. There's a million small things, but those are some of the big ones.
Are there any key acronyms we should get out of the way in terms of the alphabet soup, just so that we don't lose any of our listeners here? Like RCP seems to be important, SSP. Just before we drop any of those acronyms, like anything we should define quickly for people?
Yeah. So a couple major acronyms. So RCP stands for Representative Concentration Pathways. And those were the old sort of warming scenarios, or concentration scenarios used to create warming scenarios, to be precise, that were used in the last IPCC report, the one that came out in 2013, the 5th assessment report. The SSPs are their replacements. So they're sort of new future emission scenarios and associated warming scenarios that were produced in the lead up to this report and were used in all of the new generation of climate models. And those have various numbers behind them. So we talk about like SSP 1, 2.6 or RCP 2.6. The 2.6 number reflects the amount of radiative forcing, which is essentially a measure of the amount of watts per meter squared. It's a measure of the amount of heat trapped by greenhouse gases in the atmosphere in the year 2100. So RCP 2.6 means that there's 2.6 watts per meter squared of heat being trapped by greenhouse gases in 2100. RCP 8.5 means there's 8.5 watts per meter squared.
Just for, I think that's relevant, that 8.5 number, because I think a lot of the sort of more doomsday predictions, the David Wallace Wells Uninhabitable Earth book, have been based upon an assumption or I mean, I guess if it bleeds, it leads. Like the more extreme pathways certainly get more clicks and are more catastrophic. Was part of this report saying that those extremes are less likely?
Yeah. So the report, and I guess we can go ahead and dive into the SSPs now because it requires a little bit of explanation. But so the report included a new scenario that was not previously used in the last IPCC report. It was called SSP3 7.0. And in many ways, it's sort of used throughout the report as the replacement for the old 8.5 scenario. The differences are primarily that the 7.0 scenario results in about 4 C warming by 2100. The 8.5 scenario was closer to 5 degrees C. And it's also a more realistic pathway, this new 7.0, in terms of what a worst case scenario might look like. And part of that is it's associated with a particular socioeconomic storyline. Right. So the SSP is more broadly, the shared socioeconomic pathways look at 5 different possible future worlds, each of which has a different set of population, economic, and technological assumptions. And they cover a wide variety of possible futures. SSP3 is sort of the dark path, as I like to call it. It's a world that's characterized by resurgent nationalism and isolationism. Countries turn increasingly inward, rely on domestic energy resources. There's a lot of regional conflicts. It has the slowest economic growth and the highest population growth of any scenario. The world remains highly poor and unequal. And it's a scenario where potentially a lot of existing climate policies get rolled back. I've taken to informally calling it Trump world. It's a world where countries are actually actively subsidizing the burning of coal, as the Trump administration tried to do. Now, this is not a particularly likely world. And in some ways, it's a lot less likely now than it seemed only a few years ago when populist movements around the world were sort of resurgent. But it's not something we can fully rule out. We could have a world that is worse than the path we're on today. And so it's useful to explore what that world might look like.
I do think it's interesting because in terms of like the kind of multifactorial impacts of climate change, we talked about that on our last episode together, but we talk about a number and it's very kind of dry and sterile a little bit in terms of, we'll have 2 degrees, 3 degrees, 4 degrees of warming, but all of the impacts, sea level rise, droughts, crop impacts, et cetera. But when you start thinking about the kind of geopolitical implications, once we hit 2 degrees, 3 degrees, the added stressors, what that might do in terms of our politics at the moment, it's great that sort of Trumpism has been rolled back, but I think there's a big risk of a resurgence of those kind of politics, especially, as societies get squeezed, as there's maybe some resource scarcity or food shocks or things like that. I hope we're not heading down that route.
Yeah, a way I like to think about it, and I actually had a great conversation about this with David Wallace Wells, who, to be honest, in his heart of hearts, is a bit of an ecomodernist himself. Where I don't really like the framing of climate change as by itself an existential risk. I think that humans live in the, coldest places on Earth and the hottest places on Earth today. We live in the Arctic, we live in the Sahara. The human species will survive whatever we do to our climate. It might not thrive, and it might even be diminished significantly in the worst cases, but it's not going to cause human extinction. But I think what climate change is in many ways is an existential risk multiplier. In a world with, weak institutions, with instability, with conflict, with poverty and high inequality, climate change can push or potentially push countries over the brink that are already weakened in a way that is not necessarily the case in a world that is more prosperous or more equal. And so in many ways, the underlying socioeconomics matter as much to the impacts we're going to get from climate change, at least on human systems, as the amount of climate change we get itself. And this is something that these new SSPs actually are really well designed to show. Because we have these 5 different socioeconomic futures, we can actually very explicitly look at what happens at a particular level of climate impact across different socioeconomic outcomes. So for example, we could look at what does a 3C warming world, which is sort of where we're on track with current policies, and we can get into why later. What does that look like in the sort of Trumpian dystopia versus a techno-utopia, where everyone is rich and prosperous and high tech, an SSP1 world or an SSP5 world? How does that compare to this SSP3 dark future? And it turns out that, the impacts of 3 degrees warming are a lot worse in a world that is poor and unequal and doesn't have access to adaptive capacity than a world that is rich and prosperous and does. And so by being able to separate out sort of the adaptation, I should say, axis from the climate outcome axis, we get to do a lot more interesting comparisons. So there's a paper a while back that found that, the sort of default outcome in an SSP3 world with no climate policy, this sort of 4C warming, is actually a lot more damaging than the default outcome in an SSP5 world, the sort of RCP 8.5, SSP5 8.5 outcome of 5 degrees warming. And that's because, 4 degrees warming in a poor and unequal world is a lot more damaging than 5 degrees warming in a rich and equal world. And that was a really interesting finding. And obviously those are both fairly extreme cases. And I think in some ways it's more interesting to look at, say 3C outcomes in both those different types of worlds. But, I should emphasize in all this that adaptive capacity is, strong for human systems, particularly prosperous ones, but not necessarily for natural systems. And so the natural world is pretty devastated in 3C scenarios, no matter what happens to, our human adaptive capacity.
I was very struck by, I think, Ted Nordhaus's Mad Max analogy, and basically saying, like, when we imagine climate catastrophe, we think about a Mad Max aesthetic or world, but that's in fact, when there is a natural disaster in a country that is completely undeveloped and poor, it is Mad Max. That's what it actually looks like. So that was an interesting reflection. It does remind me. There's a chapter in James Lovelock's book, Roadmap, Bumpy Road to the Future. I think that's what it was called. And he talks about this adaptation frame, and I guess it's kind of this like dystopian future where, and we're sort of seeing it emerging in certain places like the Gulf states, where they're sort of like techno cryosphere, air conditioned buildings, and some elements of kind of ecomodernism, which start talking about, agricultural intensification, but, producing food in vertical farms, or maybe that becomes a real necessity as we have less and less cropland available, or there's more drought. Or glaciers melting and having real water stresses or mega droughts, and needing to sort of engineer our way out of this with desalination plants. And to some degree, all these things are going to be necessary, but the degree to which we kind of it's not the kind of decouple analogy that I like so much, but the way in which you have to kind of decouple from our natural ecosystem support services and sort of engineer our own is interesting. But also, to me, it's kind of like you're kind of sailing this boat into the future, and every ton of CO2 emitted is an anchor that you're throwing behind us, and that our adaptive capacities are getting limited. Like I think I heard a quote about the impact of Hurricane Maria on Puerto Rico's infrastructure was essentially setting it back 20 years. And I think that's really where I start to worry in terms of climate change, is that it's going to really slow down our ability to adapt. We'll spend so much time sort of cleaning up the mess that we're going to have a hard time thriving and progressing into the future.
Yeah, and there certainly is, even a world where we have high adaptive capacity is one. A high warming world where we have high adaptive capacity is not a world we want, right? There's definitely a vision of a humanity that adapts but does not thrive in a high warming future amid, the ruin of natural ecosystems. And I don't think that's what any of us want our legacy to be. But I think what I also really worry about, and this sort of goes back to the SSP3 storyline, is sort of a world of lifeboat ethics, right? Nils Gilman has a good piece from, I think, 2 years back now in the Breakthrough Journal called Avocado Politics, sort of looking at how, a far right that takes climate seriously might sort of adopt a very different and very not progressive view that, we need to save ourselves, right? We need to, close our borders, make sure that, none of these poor people who are suffering can come here and sort of protect ourselves from the ravages of climate change. It's every country for themselves in a high warming future. And that's not a path we want to head down necessarily. So there's definitely interesting things there.
Yeah, we had Nils on to talk about that exact topic a little while ago. So listeners, feel free to check that out. Let's return to the report a little bit more. I think so much of the kind of new climate skepticism comes out of, the science is unsettled. It's hard to know how much to attribute natural disasters to climate change, how much of things actually changed so far. So that seemed to be one of the other elements here, is that there's a real certainty now that human impacts are the key driver of warming, and also that we have an increased ability to attribute extreme weather events to climate change, or at least their frequency. Can you break that down for us a little bit more?
Yeah. So one of the biggest things to come out of this new report was a narrowing of the range of what we call climate sensitivity. So as a bit of background, back in 1979, in the sort of very early days of climate science, there was a big report led by Jules Charney that was actually commissioned by the Carter administration. And it gave the first estimate of what's called equilibrium climate sensitivity. Equilibrium climate sensitivity is essentially a measure of, if you double the amount of CO2 in the atmosphere, which is roughly where we're headed under current policies today, without additional mitigation, how much warming do you get at equilibrium? At equilibrium being like in a few centuries, when the system sort of fully bakes in the committed warming at that particular CO2 level. And that range was given back in 1979 as somewhere between 1.5 C and 4.5 C warming per doubling of CO2, with the best estimate of around 3. Flash forward to 2013, in the last IPCC report, they said that climate sensitivity is likely somewhere between 1.5 and 4.5 C, with the best estimate of 3. So that range was effectively unchanged, at least in terms of what was given in a period of 30 years. But this report made a big change to that. They said, we now think that the likely range of climate sensitivity, and again, likely here in the IPCC's uncertainty parlance means, a 66% chance or 2/3 chance of being somewhere in that range. We think the likely range is now 2.5 C to 4 C. That's still a best estimate of 3. And that's a really big reduction. That's a 50% reduction, in fact, of the likely range of climate sensitivity between the 2013 report and this report. Similarly, they also reduced the very likely range, which is sort of a 90th percentile range, from 1 degree to 6 degrees per doubling of CO2 in the last report, to 2 degrees to 5 degrees per doubling of CO2 in this report. And that has 2 big implications. The first is that we're a lot less likely to get lucky and have climate change turn out to not be a big deal. There's sort of this lukewarmer argument that, climate sensitivity might be in the low end. We might not really end up with particularly big impacts because we might only get, 2 degrees instead of 3 degrees of warming this century on the pathway we're on today. And those sort of outcomes seem a lot less likely now than they did before. At the same time, the high end has been lowered, which means that we're a lot less likely to get super unlucky and end up at 4 or 5 degrees when we think we're going to have 3 degrees warming. And that's really good news, in part because a lot of the economic damages of climate change are centered in these tail risks, these low probability, high impact outcomes. And so being able to narrow those tails can really, reduce the overall expected damages associated with climate change. And so that's good news. It doesn't mean we can fully rule that out, right? There still is up to 10% chance of climate sensitivity above 5 C per doubling of CO2. And so these changes to equilibrium climate sensitivity also percolate down to changes in our projected range of future warming by the end of the century. So in the last IPCC report, they gave ranges of projected warming for each of the different emission scenarios. But those ranges were deemed to be likely ranges. Again, there's a roughly 1 in 3 chance that it's either going to be somewhere below or somewhere above the range of warming that they gave. This report actually ends up having pretty similar future warming ranges to the last report, the 2013 report. But instead of being likely ranges, they're now very likely ranges. So there's only a 1 in 10 chance that it's going to be outside of that.
Right.
There's also an interesting story. I don't know if you want to go into it right now about how the new report dealt with sort of some of the climate models running hot and that whole issue.
Let's get there in a second. I just wanted to make sure I've got the climate sensitivity thing down. So, I mean, it reminds me a little bit of medical research and looking at like in vitro versus in vivo drug trials, that there's just, in an organism, there's so many more variables involved, whereas you can, really narrow things down to a few variables inside of a glass beaker, essentially. And so am I getting that right in terms of that's why it's taken a while to sort of get a better sense of climate sensitivity?
Yeah, it's also just new approaches using a confluence of independent lines of evidence.
Okay.
And I should emphasize, our best estimate of climate sensitivity is still 3C per doubling CO2. That hasn't changed. It's just the uncertainty around that has narrowed substantially.
This is looking at doubling rather than a date, right? Like so much of the projections are around what's going to happen in 2100. But is this inferring that? I mean, so pre-industrial levels were like 280. So we get to 560. 560, yep. And then we're going to hit that temperature range. And if we have further increases, it could double again if we got up to 1120.
Yeah. So these are equilibrium climate sensitivity values, but they are strongly related, as you can imagine, to the 2100 warming ranges that are given in the report. And so the changes in sensitivity do end up narrowing the warming ranges as well. And that's what I was sort of talking about the likely versus very likely ranges being given in the old report versus the new one for 2100 warming outcomes. But in terms of why these climate sensitivity range was narrowed, it really was this big effort on the part of the community to try to synthesize different estimates from different sources. So there's a whole host of researchers studying what's called paleoclimatology, or the climate of the Earth's distant past. Right. And that can be used to constrain sensitivity, right? We know how CO2 and other greenhouse gases changed during the last ice age, during the last interglacial, during the Eemian, during the Paleoeocene thermal maximum, during all these different past periods of the Earth's history through climate proxies. And we can sort of use that to infer what the relationship between greenhouse gases and temperatures might be and what the bounds of that are. Similarly, we have observational evidence. We know how the world actually warmed over the last 200 years in terms of, surface temperatures for the last, 70 or 80 years in terms of ocean heat content. That can be used as its own sort of line of evidence to try to constrain our estimates of climate sensitivity. And then we have better understanding of various physical processes like clouds and other dynamics that themselves can constrain climate sensitivity. And so the idea is if we can take multiple independent or mostly independent lines of evidence from different types of studies and combine them, the joint sort of distribution of each of those will be narrower than the distribution of any individual line of evidence. And it's really that insight that is the primary thing that allows us to narrow the range of sensitivity that's in this report.
From what I understand, another element of the report that increases our confidence in our abilities to model climate is that when we retrospectively apply our climate models, we're finding that they're quite accurate. Is that correct?
Well, yes. That doesn't by itself narrow the range of sensitivity, but it does give us confidence that, models broadly are working. So this is actually the part of the report I directly contributed to. I published a study last year that found that essentially took all of the climate models that have been built since 1970. 1970 was the first time there was a climate model published that actually said, we think this is going to happen by this date. We think the world is going to warm 0.6 degrees centigrade by the year 2000 relative to 1970. So that was the first. And then there was, 17 other ones we found up through the 2000s, after which it becomes a little bit harder to sort of evaluate the future performance of these models just because the time period is so short. But so we took all these 17 models between 1970 and the early 2000s. And we said, okay, what did these models say would happen in the years after they were published? So obviously they can't know the future, right? So it's a out of sample projection by the model. And what actually happened in the real world? And it turns out that the models did really well at projecting what warming would actually happen in the real world. 11 out of the 17 models we looked at were essentially spot on. They were statistically indistinguishable from observed rates of warming. And the other ones were not that far off. Some predicted 50% more warming, some predicted 50% less warming. I think of the 6 that were off, 4 were on the high side and 2 were on the low side of observations. And part of that is not necessarily due to the fact that the models got the physics wrong. Because if you're trying to model the future climate, you're really dealing with 2 separate questions. The first is, how does the climate system work? And that's a question of physics. You can get a better model over time by improving the physical representation of the climate. But the second question is, what will people do? How much will we emit? And that's not a question of physics. That's a question of human behavior, of economics, of politics, of demographics, of socioeconomics. And so, you could have the best climate model in the world in the 1970s. Not that we did, but, hypothetically, and it still could give you a bunk projection if you assume that people emit, 50% more greenhouse gases over the next 50 years than they actually did. And so we also did a test where instead of looking at how well the models performed in terms of predicting the warming that actually occurred, we looked at what models said should be the relationship between warming and CO2. Really all radiative forcings, but effectively CO2. What does the model think should happen, unit of warming per unit of CO2? And then what happened in the real world in terms of how much warming we've experienced per how much CO2 we've actually emitted, or how much CO2 has actually gone up in the atmosphere. And the nice thing about that metric is that it sort of normalizes for the fact that you can get the amount of CO2 wrong, but that fundamental relationship is still going to be mostly right. And when we did it that way, we found that 14 out of the 17 models agreed with observations. So climate models, have been pretty accurate in the past, which is particularly impressive when you go back to the 1970s, because back in the 1970s, we didn't really have a good sense of what global temperatures were doing. Like, we hadn't gone around the world and digitized all the old logbooks from ships. There was no estimate of ocean temperatures at all, which is 2/3 of the planet. And almost all the land temperature observations that scientists had collected at the time were from the Northern Hemisphere. And so scientists in the early 70s actually thought the world was slightly cooling, at least it had been for a couple decades. And so you have these papers essentially saying, we think this cooling trend is going to reverse itself and the world will warm substantially in the next 30 years, which is a pretty bold claim to make. Like, it's one thing to be like, the world has been warming at 0.2 of a degree per decade, and we think it's going to keep warming at 0.2 of a degree per decade. That's an easy prediction, and that would have been a roughly right prediction. But to say that the world is cooling and it's going to change course and warm is a much more bold one. And so it's particularly impressive that those models ended up getting things right.
Yeah. So, again, I think in terms of one of the challenges of science communication around climate change is, these degrees of warming, this global average temperature rise. And I mean, if you just add 1 degree onto all of the temperatures that you experienced throughout your life, this year, or maybe when you're a bit younger, it doesn't sound all that concerning. Obviously, in Western Canada, for instance, we're seeing rates of temperature rise that are 3 times that of this global average temperature. But in terms of focusing on more concrete impacts, I was seeing an article on your Twitter page that was bringing, I think, the resolution of sea level rise into a little more focus. Because when we look at the actual impacts, I think that's when we start to have a better understanding as everyday human beings what the impacts are likely to be, rather than just a degree of centigrade. So tell me a little bit more about what we know about sea level rise, how much we've had so far, what the projections are. Are those ranges more understandable, and is sea level rise is going to stop at 2100, or?
So to back up a little bit, you raise a really great point that no one lives in the global average, right? In fact, the global average is oceans, because the world is mostly oceans. And so when we talk about these global average temperature increases, they're not very meaningful to people. But what you should keep in mind is 1 degree of global average temperature increase is 1.5 degrees over land on average. And land is obviously where we all live, because land is warming 50% faster than the oceans. And it's 3 degrees centigrade of warming over the high latitude regions like the Arctic, which are warming much faster than the world as a whole.
Wow.
And so one thing that always grounds me in terms of the magnitude of these changes is the last ice age, which I think everyone would agree was a very different planet than we have today, was only about 5°C cooler in terms of global average temperature than the Holocene, than the temperature of the planet today. And so if 5°C is the difference between the middle of the last ice age and today, and though that's the magnitude of climate change that, on the very high end, we could potentially see this century. It's unlikely, thankfully, now that we're not going to burn all our coal, but it's certainly within the realm of possibility of things that could happen.
We had like a 2 kilometer thick ice sheet, like from where I'm broadcasting to you from.
Exactly.
Maybe it was even thicker. Right.
So there are really big changes. It would be a different planet if we warmed, 4 or 5°C this century. But we'd probably commit ourselves to more warming after that, because you'd have, very large losses of permafrost and things like that. But in terms of sea level rise, sea level rise has long been a challenging thing to effectively model, in part because, it is really complicated. We don't we have a lot better measurements now than we had a decade ago of what's happening with ice sheets and all the dynamical processes involved there, but we certainly don't have a perfect understanding. We know that the ice loss from Greenland and the West Antarctic is speeding up substantially. It's now contributing more than half of the sea level rise we're experiencing versus, a quarter of that a decade ago. Previously it was mostly thermal expansion of water that was driving sea level rise. Now it's mostly loss from ice sheets. But exactly how those ice sheets will change in the future is still an area of huge scientific debate. And so, the IPCC has a set of fairly, I'd even say conservative estimates around sea level rise changes in sort of their central scenario. And sort of what they say is that in a world that's in line with current policies, sort of where we're headed right now, we'd probably expect somewhere around 2 feet or so of sea level rise by 2100, which, is a decent amount. The world has already experienced about 3/4 of a foot of sea level rise since the 1800s. But that will continue accelerating after 2100, even if temperatures stabilize, because, there's big lags in ice sheets. They absorb an enormous amount of energy to melt, and, that they sort of unfreeze slowly. Mm-hmm. And so ultimately, if you look by 2300, in a current policy scenario, we'll probably end up having anywhere between 2 to 5 meters of sea level rise. And even in a world where we cut global warming down to, Paris Agreement targets of well below 2 degrees, we'll probably still have somewhere between 0.5 meter and 3 meters of sea level rise by 2300.
I want to understand, from the paleoclimate models, this isn't necessarily something that's just going to occur in a nice steady rate, but there may be big jumps to it. We might see big rises over a decade or slower rises over other decades. I think when we imagine these things, at least as a non-climate scientist, we tend to think of them as very basic, simple mathematic functions, but there could be some interesting waves and fluctuations in there.
You certainly could. I mean, it's hard to get good paleoclimate sea level rise estimates on the time resolution of the decade. We're mostly talking century scale estimates just in terms of, how precise we can get in terms of dating things. So it's really hard to know if there are huge shifts in the course of a decade. But certainly, even the rate of sea level rise we're having right now on a century scale is projected to be quite fast. And there's also, still some big unknown processes. There's a huge debate happening in the sea level rise and more broadly the ice sheet modeling community around what's called MICI, another acronym to define. MICI refers to marine ice cliff instability. And so there's sort of 2 different schools of thought on sea level rise. There's one that says, okay, we're going to have thermal expansion. We're going to have top-down melting of ice sheets. We're also going to have some, additional flow speeds through lubrication of the base of ice sheets. But those are the main processes that are involved. And those are what give you those ranges that I was talking about earlier. There's another group of researchers who say, well, wait a minute, there are potentially other things that work right here as well, particularly this idea that as glaciers calve into the oceans and are flowing faster, the height of the ice that's falling into the ocean increases as the glacier,
moves forward,
flows more into the ocean more. And so you get these higher and higher cliffs that are left over as the glacier falls into the ocean. And those cliffs become increasingly unstable the higher they are. And so there's this idea that process could be sort of self-reinforcing, that as the glaciers fall into the ocean, the higher and higher ice cliffs that are left behind are going to fall faster and faster. And if you try to model that, you can end up with, potentially up to twice the rate of sea level rise you would have without that mechanism. Now, the other side would say, well, wait a minute, we don't really have a great physical understanding of that process. It might sound, on its face simple, but in reality, it's a lot more complicated. And our paleoclimate estimates don't necessarily support, mechanisms that are quite that fast. And then the other side says, well, we don't necessarily have the best paleoclimate records, and there's still big uncertainties here. And so it's sort of a big debate going back and forth. The IPCC sort of tried to wade into the middle ground of that by using sort of the community consensus estimates without marine ice cliff instability mechanisms as their base estimates, and then sort of showing a, shaded range of possibilities if you account for marine ice cliff instability models. But it's a big unknown. Anyway, I think the point is, regardless, we're going to be committing ourselves to multiple meters of sea level rise in the future. If it's, tens of meters, eventually depends a lot on some of these unknown mechanisms. And of course, ultimately on how much warming we have. Because again, a world that is at 4C warming is going to commit us to a lot more sea level rise than a world that is at 2C warming.
Yeah, I mean, I think we'll move into talking a little bit more about some of the arguments of the lukewarmists, but particularly with sea level rise. Certainly if you have more resources, you're a wealthier country, there will be some increased ability to adapt to sea level rises. But sea level rises of these magnitudes, particularly that just don't stop, that keep going on, where you need to raise your dikes, year after year. And with the distribution of human populations along shorelines, like what's your take in the face of that kind of lukewarmist argument that, hey, if our societies are rich enough, we can be resilient to this, it's no big deal?
I mean, I think there's some truth that if we're rich enough, we'll be resilient. I think it also will cost an enormous amount of money. I mean, seawalls are not cheap, and adaptation more broadly is not cheap. It comes with a cost. It also comes with the loss of a lot of our beaches, which we value. But also, what the impacts of sea level rise are less like the ocean is increasing by an inch every year and slowly inundating buildings. It's that we have storm surges today that are, 5 feet of storm surge. If you add 3 feet of sea level rise on top of that, it becomes much more disastrous. It reaches much further inland. And the problem is, even if you build a seawall that's higher and higher, if you end up having that freak hurricane that gives a storm surge that tops your seawall, you're going to have an enormous amount of inland flooding in a world with higher sea level rise, because you're not building up the entire surface of the area behind that seawall to match, right? Seawalls are imperfect defenses, particularly in areas that are subject to tropical cyclones. And even places that should be super rich and have good defenses, like New York City, got a big wake-up call with Hurricane Sandy, or Superstorm Sandy, I should say, because it wasn't technically a hurricane when in New York, but Superstorm Sandy, where they did have huge impacts from storm surges, even in the world of today's sea levels.
So Zeke, for you, like, what are your beyond the numbers, beyond 1, 2, 3, 4, 5 degrees, in terms of those real world impacts? Like, give us your top 5 climate impacts that you're concerned about. We talked about sea level rise. I'm imagining that's one of them, but can you hit us with a couple more just to flesh that out?
Yeah, so sea level rise is one. Extreme heat events are another. As we saw in the Pacific Northwest recently, or in Canada, where they had 121 degrees record. Extreme heat is deadly. Our best estimate is that over 600 people died from that event, and that's in a place that has a lot of adaptive capacity from extreme heat. If you start talking about tropical regions, you could have really devastating events that result in a lot of mortality, particularly in a world that is poorer, where there isn't ready access to air conditioning for everyone. Again, you can't really separate out climate impacts from adaptive capacity. They're strongly interrelated. But those risks are real, and they are increasing.
And that's this concept of like wet bulb temperature, where you literally cannot survive if you've got a thermometer wrapped in a wet sock and swing it around your head and it's registering more than, I think, 37 degrees, right? Like you can't live for more than a few hours if you're hitting that temperature. We do hit that temperature occasionally, but like much larger areas of the earth will be subject to that combination of heat and humidity that's just incompatible with life without air conditioning.
Yeah. And most of the parts of the world where that temperature is hit right now, like, people have systems in place to try to respond to it. They don't work outside in the middle of the day when it's that hot outside. Right. But as those sort of temperatures start hitting places of the world that have not historically adapted for those sort of conditions, it's much more likely you could end up with, a heat wave that leads to a huge amount of mortality because, farmers don't let all their farm workers off the field because they've never experienced something like this before. They don't know what to expect. They don't know that people might literally drop dead from working in the middle of the day in these sort of conditions. And so, to
the degree that was sort of part of the explanation for why so many people died, at least in Western Canada, was because people don't have AC there. It usually doesn't get that hot. I mean, they probably will get it now, but
yeah. Well, and it's not just, daytime conditions. Particularly if you're elderly or if you're in poor health, like being indoors in 90 degree plus heat all night can be deadly. Yeah. We saw a heat wave in Europe in 2003 that killed tens of thousands of people, mostly elderly, in large part due to indoor nighttime temperatures in places without air conditioning. So, we can again, mitigate these impacts by getting more people air conditioning. But there's no guarantee we're going to live in a prosperous, equal future. And certainly there's a big risk that there are a lot of people who remain poor, who don't have access to these adaptive capacities, who do suffer greatly. And ironically, are also generally the people who are least responsible for this problem to begin with, because they're not the ones who are emitting tons of CO2.
Right. And there's the air conditioning paradox where, unless you can really decarbonize your electricity, you're burning more fossil fuels to keep yourself cool. So we've got sea level rise, extreme heat. Give us a few.
Yeah. So, one that's a little close to home here in California is wildfires. We've seen a dramatic expansion of fire weather around the world as temperatures rise. And that's less due to drought per se, and more due to vegetative moisture. So the drier the vegetation is, particularly in places like California or the Mediterranean or Australia that have sort of a monsoonal type climate. You have long parts of the year where it rains very little or none at all. The drier the hotter it is, the drier the vegetation gets. And when you have very dry vegetation, you have the potential for very rapidly spreading and catastrophic wildfires that are much harder to control than if you have wetter vegetation, because they spread so much faster and are much more likely to reach up into the canopies of forests and actually kill the trees. Here in the Western US, we have forests that are nominally adapted for frequent low-level wildfires. In fact, prior to colonization, the native communities here used to burn about 4 to 6 million acres a year, which is roughly how much burned last year in California, which was, the worst fire season in modern history. That was every year, but those were controlled burns. They were low-level burns. They were done, when conditions were such that they wouldn't spread out of control. And they were done so frequently that they cleared a lot of the fuel that had built up in these forests. And so, with conditions as dry as they are right now, we still do have a fuel loading problem, and we need to do a lot better job taking care of that. But also, it's just a lot easier for these fires to spread out of control than it was before. And so, wildfires are really dangerous, both because of, direct, fire risks, but also because the smoke they cause is a huge health hazard. In fact, the smoke from wildfires kills many, many more people than the wildfires themselves do. And so having a smoky season now in California, having to check the air quality every day before you go outside, it's a big change. And that's a big impact in certain parts of the world.
Mm-hmm. Mm-hmm. One thing that came into the news recently was the AMOC, the Atlantic Meridional Overturning
circulation.
Yeah, I mean, basically, that conveyor belt of water that makes...
Not the Gulf Stream, by the way.
Yes,
the Gulf Stream is a different thing.
So tell us,
even though the media always confuses
that's been in the media a lot. It's slowing down. I understand from this report there's a low chance that it will collapse before 2100. But tell us about that and its predecessor, the Younger Dryas event. I just think Younger Dryas sounds cool, but apparently some people say it coincided with the birth of agriculture. I mean, we don't need to go into tons of detail here, but I just think it's a kind of demonstration of the system.
As a bit of background, a lot of ocean circulation is driven by salinity. And the reason is, as surface water evaporates, or as water evaporates off the surface of the ocean, it leaves the salt behind. Salt doesn't go up with water vapor into the atmosphere. It doesn't rain salt water, thankfully. And that means the surface waters of the ocean become saltier, and salt water is more dense. So those denser surface waters fall down, they're replaced by deeper water, and that overturning drives ocean circulation. And areas where, the water's sort of been traveling for a long time before it gets dense enough, can drive sort of this ocean conveyor belt. And so there's certain places where you have a lot of overturning, we have very salty water that just reaches that, threshold of density where it starts to sink. And one of those main areas of overturning is in the North Atlantic, sort of southeast of Greenland. And so what happened in the Younger Dryas period, which was a period about 14,000 years ago, 14,500, I don't recall the exact date. It was the end of the last ice age, and a huge freshwater lake had formed in the northern part of North America called Lake Agassiz. As the glaciers melted, it formed this, inland sea, essentially, of freshwater, because the glaciers are all freshwater. And at some point, the final layer of ice sheets between that freshwater sea and the North Atlantic broke, and it was like the biggest dam on Earth. And this giant freshwater ocean or freshwater sea poured into the North Atlantic very rapidly. And it turns out that when you put a ton of fresh water into this salty surface water, it becomes less dense, it no longer sinks, and you stop this overturning that drives the ocean circulations. And so what happened in the Younger Dryas is the thermohaline circulation, or the AMOC, shut down. The ocean conveyor belt stopped. You stopped transporting sort of warmer water from the tropics up to the North Atlantic, and you sort of plunged parts of the Northern Hemisphere back into a mini ice age. Because, the currents that bring warm water up north that make, the climate of the UK not similar to the climate of central Canada, are themselves, driven in part by this thermohaline circulation, or by the AMOC. And so that's not going to happen today. There's not a giant freshwater sea that's going to pour into the North Atlantic all at once. What we're seeing today is at a much smaller scale, but it's a similar process. So freshwater melting off the ice sheets of Greenland is pouring into the North Atlantic at increasing rates. It's leading to fresher surface waters there. And we're already seeing this very interesting cold spot to the southeast of Greenland. If you look at a map of global warming over the past century, every place on Earth has warmed except for the ocean southeast of Greenland. It is this very distinct warming hole. And the reason for that is because the circulation has already slowed down, and it's caused regional cooling around there. And so this slowdown might accelerate. It likely will not result in actual cooling. We're not going to plunge the Northern Hemisphere back into a little ice age, simply because the magnitude of the changes are slow enough that they're going to be more than overcome by global warming. But it'll certainly lead to a lot less warming than we would otherwise have in areas like the UK or the Northeast US, or areas bordering the North Atlantic more broadly. That's actually not necessarily a bad thing. It's good to have less warming there. Where it is potentially a bad thing, though, is this doesn't just affect regional temperatures. The AMOC also has big effects on precipitation patterns globally. And so you'd expect like more drying around the Mediterranean, potentially more drying in the Southwest US, wetter areas in some tropical bands. You have sort of secondary effects of this, particularly on rainfall, that could be much more impactful. This isn't a climate tipping point that ends the world. It's something that, the impacts are still being sort of fully fleshed out, and there's some uncertainty around it. But it's definitely something to keep an eye on. And models generally suggest that it's unlikely to collapse this century. There was sort of a paper by a single author that got a lot of media attention a couple weeks back that suggested might actually collapse this century or slow down much faster than previously thought. Other scientists have pushed back on that. As with anything in science, it takes a while for a new consensus around these things to emerge. But certainly the best state of our knowledge at the moment is that this process might gradually slow down over the next century, and is unlikely to completely collapse, but certainly could affect rainfall patterns in a meaningful way.
So I think for the layperson, this is all very complicated and hard to wrap your head around, right? And certainly there's been a number of books that have come out recently. I think probably, I forget his first name, I think it's Steve Koonin's book, Unsettled, came out recently. And it's really describing the state of climate science as not as settled as we're being told, that, the media is not accurately representing the findings of climate scientists. And there's a bias towards, again, if it bleeds, it leads. I'm not sure if you've come across Koonin or read his book or have a sense of his arguments. It seems like this latest report really has brought things into a much more focus and settled the science more. But yeah, if you do have any thoughts on that, I think that'd be very, very useful.
Yeah. So I think there's some truth that the media can focus on the sensational. I think everyone agrees on that. We particularly see this with some of these high emission scenarios I was talking about earlier. At the same time, I'd argue that folks like Koonin, who, is a physicist, an emeritus physicist, people who sort of go outside of their field and have, strong opinions about other people's fields, also, misrepresents the science pretty significantly. Koonin gets a lot of things wrong in his book about sea level rise, about extreme events, about, rates of historical warming, about the performance of climate models. I think something like the IPCC, which is this massive sort of synthesis of tens of thousands of papers done by 1,000 scientists, really provides a good, reasonably conservative, because they're not like going out on a limb with the latest sort of paper with a new finding that hasn't been corroborated by others, but provides a reasonably conservative estimate of where we are with the science. And it paints, a pretty grim picture. And I think that it's not the end of the world, and it's not good for us. And it's, a worse problem than some folks like Koonin paint. So I'd say that, if you think that climate science, might be more uncertain than we think, read the IPCC report. It lays out where the uncertainties are, and there are real uncertainties in a lot of these things, and we should be clear about them. But it also paints where the certainties are and where we've gotten a lot more certain over the last decade. Because where climate science was 30 years ago and where it is today is enormously different. We've made huge leaps and strides in understanding the Earth system. And these fundamental issues that we were concerned about 30 years ago, we've only gotten more concerned about in the time since.
From what I understand, Koonin's largely basing his argument off of the 2013 agreement. Is he doing a fair amount of cherry picking there? Because he says, listen, I'm only just citing the IPCC here. There's a very deliberate rhetorical strategy that he's taking. How are his arguments methodologically flawed? Is it cherry picking? Is it out of date science? Again,
it's a combination of both. A lot has changed over the last decade, but it's also cherry picking. So I'll give you a good example. Koonin argues that, sea levels were rising just as fast in the 1930s as they are today. And there's 5 major reconstructions of historical sea levels based on tide gauges. One of those 5 agrees with Koonin's argument. The others don't. The others show that it's, clearly rising faster today than it was in the 1930s. And, if you look back over the last 3,000 years, as we have some paleoclimate reconstructions now, you can clearly see that sea levels now are, far higher than they've been in any time in sort of modern human history. So, I think you can always cherry pick the one data set of many data sets that agree with the point you're trying to make. But it's a little disingenuous if you don't contextualize that within, what else is out there too. And so I think, we need to acknowledge that there are uncertainties in these things, but we also need to acknowledge that what we do know and not sort of go out of the way to make a case that downplays the potential severity of climate impacts, just like we need to make sure we don't go out of our way to cherry pick the worst case outcomes and only focus on those.
Yeah, it's a little reminiscent of some of the great sort of COVID complacent communicators out there right now in terms of cherry picking and avoiding some of the kind of. It's not really a consensus because it's such a rapidly changing environment that we're under, but there's certainly feels a bit reminiscent. You can find and cherry pick certain figures that can make a compelling argument. If you frame it well within a book or a podcast, it can have a big impact to an audience that's frankly not very well educated or informed. So basically, to summarize, you're saying the IPCC is pretty damn reliable as this collection of actual climate scientists, not physicists that are opining based upon maybe a bit of a biased review of the literature.
Yeah, and I'd say the IPCC is also pretty conservative, right? You're only going to get that many scientists to agree on something if there's very strong evidence for it, because, we scientists are a very disagreeable lot, and no one gets their career-defining paper in Nature by finding the same thing that everyone else has previously found.
Right, for sure. So maybe just to kind of wrap it up, I do find within ecomodernist circles, there's a real disdain for alarmism and catastrophism. We do tend to be quite solutions focused. I think we tend to be very pragmatic and understand things like Václav Smil's work, which illustrates that energy transitions are clumsy and slow, that we never really truly transition past older forms of energy. We're still burning wood all over the world. These things take time, and that things like degrowth, for instance, are not going to deliver a world where we can adapt and may not even be that impactful in terms of changing emissions. But with reports like this and looking at the multiple variables, we went into a few of the ones that concerned you most. I mean, this is very, very concerning stuff. And I think I'm a little concerned with the kind of lack of boldness in some of our policy proposals within the eco-modernist world because, again, of that sort of, well, let's not dip into alarmism. I'm not sure if you share that analysis or that outlook, but, in terms of, I guess, being accused of being overly pragmatic, like the shape and scale of scope and scale of what's required of the kind of economic investments we need to make in order to meaningfully reduce our emissions. It's daunting, right? What are your thoughts on I guess on eco-modernism, on alarmism, and on maybe how our politics needs to change, how we need to think and communicate about our policy proposals in the face of things like this report, which are illustrating a pretty stark future.
Yeah, I mean, I think it's quite possible to be, concerned without being overly alarmist. And I think it's possible to advocate for sort of technologically optimistic policies to help solve these problems without embracing degrowth. I have a piece that I published earlier this week, actually, over at Breakthrough, called, Flattening the Curve of Future Emissions. That's sort of all about all of the progress we actually have already made over the last decade in sort of making some of these worst case outcomes a lot less likely. Global coal use peaked back in 2013, is now in structural decline. We slowed the rate of emissions growth from 3% a year in the 2000s to 1% a year in the 2010s. Clean energy has been made cheap in a lot of cases. And it's, not a panacea, but, we've made huge progress on the costs of renewables, the costs of electric vehicles. There's a huge amount of money being plowed into advanced nuclear these days, and hopefully we'll see some big things there. So, and to be honest, the solutions that are put forward in the IPCC reports, particularly in Working Group 3, are fundamentally eco-modernist. They're envisioning a future that is prosperous, that is equal, that is, better for all of humanity, with high economic growth, where we simply replace our fossil fuels with clean energy sources. And so I think, we as an eco-modernist community need to embrace positive visions, positive technologically optimistic visions of the futures, like the ones that are in these IPCC integrated assessment models. We can debate about exactly which mix of energy sources is going to be optimal. And, any prediction about future technology costs is probably going to be wrong, since, the past is littered with the bones of failed energy model projections. But at the same time, it's definitely possible to envision a world that is rich, that is prosperous, that is equal, that is high tech, and where we limit warming to below 2 degrees. We just need better policies and better technologies to get there.
Right. You were mentioning there is an SSP pathway that is more sort of degrowth in focus. I mean, just I guess in closing, give us your sense of what a degrowth model would look like in terms of both mitigation and adaptation.
So all of the SSPs are very strongly growth focused. I think even in the sort of Trump world, SSP3, that's the poorest of all of them, global GDP still, roughly triples by 2100 and increases, 5 to 8-fold in some of the sustainability focused SSP1 scenarios or the SSP5 scenario. So these are all very prosperous worlds. The per capita income or per capita GDP globally in 2100 is like $120,000. There aren't really any degrowth worlds in the current energy system modeling literature. There have been a few papers published recently by some folks arguing that there should be. And we'll see if, any energy system modelers actually want to deal with that for the next time around. But at least currently, it's sort of prosperous futures all around in terms of the underlying models in this IPCC report.
What's your sort of, if you had to kind of spitball on this, or your sort of main critiques, and we can't do a whole podcast on degrowth here, but maybe just in a minute or two, what are the fundamental problems of thinking we can degrow our way out of climate mitigation and adaptation?
I mean, the fundamental problem is that we've already absolutely decoupled emissions in the rich world, and they're decreasing. It's the poor countries reaching the standard of living that we take for granted, and lifting billions of people out of abject poverty. That's going to be the driver of future emissions. And yes, I'm sympathetic with arguments that rich people don't necessarily need to consume as much. And I think people should be free to make choices to consume less. And in some cases, governments might even want to restrict harmful activities or put a higher price on them that lead to less consumption. But at the end of the day, what matters is not, the rich world. It's the folks who are, want to be and should be, to be honest, as wealthy, as prosperous, and have the same opportunities that we have today. And I don't think degrowth is a good solution to that problem. I don't think you're going to be able to convince an India, or for that matter, a sub-Saharan Africa, to forgo the level of comfort and quality of life that we take for granted. And I don't think you're going to convince the rich countries to make enormous transfers of wealth to the poor countries that would allow for some sort of equitable middle. I think it's similar to the argument that we need to overthrow capitalism to solve climate change, which, maybe if someone were the dictator of the world and could create a perfect system, that could work out, but it's not the world we live in. And sort of arguing for these utopian or potentially dystopian solutions, in practice just ends up kind of being an excuse for doing nothing.
Mm-hmm, mm-hmm. Okay, Zeke, this has been fascinating, a real masterclass. I'm coming away from this with a much better sense of the state of the climate and a sense of what this report means for that. So it's been a very busy week for you, as you were saying. You're holding on to your voice quite well. It's not as hoarse as I expected, but thanks for spending some time with me and my listeners. I really appreciate it.
It's great to be here.
All right, man. We'll catch up again soon, I hope.